In this video, we're going to continue looking at compact sets, and we're going to prove that every compact set is bounded. So, proposition is compact implies bounded. A compact subset S of a metric space is bounded. In particular, if you take S to be the entire metric space, every compact metric space is bounded. Let's prove this. So we need to show that there is some R greater than 0 and a point P in the space E, so let's say E is your metric space, such that S is contained in the ball of radius R centered at P. That's what it means to be bounded. Well, we of course are going to have to use the compactness somehow. So we need an open cover of S. And the idea is to just take, well, pretty much any open cover of S. So how do we construct an open cover of S? For each point in your set, just take an open ball centered at that point. So for each P in S, the ball P sub 1 of P, so that means the ball of radius 1 centered at P, okay, the open ball contains P, so S is contained in the union of the open balls of radius 1 centered at P, for P and S. Okay, so S is contained in the union of these open balls, and so therefore the collection of open balls is an open cover of S. So since S is compact, there are a finite number of points. There is a finite collection of points in S, say P1 up to Pk, such that S is contained in the ball of radius 1 centered at P1, union, the ball of radius 1 centered at Pk. Right? That just follows from the compactness. So at this point, we're pretty much done because S is contained in the union of a finite number of open balls, and that is a bounded set. Let's make sure we understand why this is a bounded set. Why is the union of a finite number of open balls a finite set, a bounded set? Well, okay, so you have your P1 to Pk, so I'm just going to pretend for the purpose of this picture that K is 3. So you have this ball of radius 1 centered at P1, and then you have this ball of radius 1 centered at P2, and then this ball of radius 1 centered at P3, and the claim is that this is a bounded set, that the union is bounded. Well, okay, why is that true? If you just take any point P1 in your set, so these all have radius 1, okay. If you just take any point, say P1, then if you go out, okay, to P2, that's the distance between P1 and P2, and then you have to add a radius 1. And then from P1 to P3, you add a radius 1, and if you take the open ball, which is of center P1 and whose radius is greater than that, so this would be the distance between P1 and P2 plus 1, This is the distance between P1 and P3 plus 1. And then you take an open ball of radius larger than both of them, centered at P1, okay, it should contain the union. So it should contain all three of these open balls. I mean, that's the idea. So we will show that this union is bounded. This is like a little lemma, right? I mean, at this point, the problem, since S is contained in this finite union of balls, the problem just reduces to showing that this is a bounded set. So we'll take R to be just any number larger than the maximum of the distance between P1 and P2 plus 1 up to the distance between P1 and Pk plus 1. Or alternatively, we could just take the maximum of the distance between P1 and P2 up to the distance between P1 and Pk, and then just add 1 to that, right? It's the same thing. But anyway, this is also okay. So let's check that if you take any Q in your union, that Q is contained in the ball of radius R centered at P1. So let Q be an S. Okay, well, since S is contained in the union of these open balls, there exists I from 1 to K such that Q is contained in the ball of radius 1 centered at Pi. So the distance between P1 and Q, well, by the triangle inequality, that's less than or equal to the distance between P1 and Pi plus the distance between Pi and Q. And the distance between Pi and Q, it must be less than 1 because Q is in the open ball of radius 1 centered at Pi. So this is less than or equal to the distance between P1 and Pi plus 1, which of course is less than R because we define R to be the maximum of all these numbers. So the distance between P1 and Q is less than R, so therefore Q is contained in the open ball of radius R centered at P1, and since Q was arbitrary point in S, that shows that S is contained in the ball of radius R centered at P1. So in particular, S is bounded, and that's the proof. So overall, still a fairly standard proof, I think. I mean, use the compactness. So the idea is you want some open cover. So the idea is for each point in your set, you just take an open ball. Here I just took open balls of radius 1, and then take the union. So the collection of open balls is a open cover of S. So when you take the union, there's some finite collection such that S is the union of that. So S is contained in the union of a finite number of open balls, and then it's fairly standard technique to prove that this is a bounded set. So this technique is definitely worth knowing that when you have a finite set, you just take a point and then take the radii and then take the maximum, right? Add 1. Well, whatever the radius of those balls were, in this case it was 1, and then showed that the union of those open balls is bounded, and so S is bounded. Okay. So once I took capital R, I just took Q and S to show that S was contained in this ball of radius R centered at P1.